Okay, hello. So here's the next part in the video series on additional maths. The topic for this video is trigonometry, and I'm going to try and make this video quite short because generally speaking the knowledge you need in this section is quite limited, and most of the students who would be studying this are going to know, if not all of it, then almost all of it already. Of course you might not know all of it, so what I thought I might do to start with is, instead of starting with the material, I'll start with looking at the syllabus and the exam questions. So you can have a quick look at that, and it might help you to decide how useful this video is likely to be for you personally. So hopefully you can see here, and I'll just read it out. We have from the syllabus, these two boxes are taken from the syllabus document. Firstly, we need to know the 6 trigonometric functions of angles of any magnitude: sine, cosine, tangent, secant, cosecant, cotangent. So it's secant, cosecant and cotangent there. So let me underline or just identify clearly these three: secant, cosecant, cotangent. So they're usually written sec, cosec and cot for short, because as you know the other three are written for short: sin, sine, cos, cos, and tan, tan. And basically the relationship between these is the reciprocal relationship. Actually, that connects to that, that connects to that, and that connects to that. So I'll explain that in a minute, because that's one of the few things that a lot of students won't already know. The next part of the syllabus talks about concepts of amplitude and period, and focuses on a very specific type of graph, which is the general graph of the form A times a trig function of b times x plus a constant c. So I'll show you in a minute. Hopefully you will understand what those graphs look like. Then the other part of the syllabus, this part here, is just talking about some simple definitions and formulas. We all know this formula, and it follows from this formula that we can get this formula and this formula. And you don't need to try and remember these formulas, because they're on the formula sheet and they're very obvious anyway. As long as you remember this key starting formula, you can get the others. Then it talks about solving trig equations, and we'll look at some examples of that, and proving formulas or proving identities. Remember from the video on polynomials the meaning of the term identity. Okay, now I'll very briefly show you a couple of examples. Here's one. This is proving an identity. This is proving another identity: 1 plus sec theta times cosec theta minus cot theta equals tan theta. Then we have the solving of an equation here. Shouldn't be too difficult for most people. And then the other two, I think, sorry, this one is about drawing graphs: a sine bx plus c, similar to this here. And the last one is again solving equations, maybe slightly more difficult, but not very. So what I'll do is I'll briefly review the meaning of secant, cosecant, cotangent, and then I'll talk quite a bit about graphs, and then we'll talk about solving equations in the context of these examples, which I took from various past exams. So these are exam questions. Okay, so let's go into the main. Sorry, just a quick thing there. Let's go into the main section, and we're going to talk about first of all definitions. Cosecant x is defined to be 1 over sine x. Obviously sine x cannot be 0, secant x is defined to be 1 over cosine x. Obviously, cosine x cannot be 0. And lastly, cotangent x is defined not as 1 over tangent x, but as cosine x over sine x. Sine x again cannot be 0. Now it's an important point that this is not defined as 1 over tan x, although it usually is the same thing, because consider the angle, now let me think, consider the angle 90 degrees. What's the tangent of 90 degrees? So your answer should be it's not defined. Now just for reference, let me very roughly sketch tangent x. There it is. I do emphasize a lot of my graphs will be a bit rough because it's difficult to draw on this. Okay, so if this is tangent x, you see it has no value when x is 90 degrees, and it has no value because cosine x is 0 at that point. However, if we look at cotangent 90 degrees, does this have any value, or is this undefined also? Well, the answer is cotangent x is defined, cotangent 90 degrees is defined as 0, because cosine 90 is 0 and sine 90 is 1. So it's cos 90 over sine 90, that's 1. So cot 90 is 0, but tan 90 is not defined. So that's why we do not write cotangent x is defined as 1 over tan x, but as cos x over sine x. And let me just show in a different colour here. This is usually written cosec. This is usually written sec. And this is usually written cot, C-O-T. Now, you may or may not have these as buttons on your calculator, but obviously you can easily calculate them using the formulas provided here at any particular time. So that's the basic definition. Let's have a quick think about the graphs of these functions, because obviously, well, not obviously, but these graphs are not really used on the exam as far as I remember, but I really think any student should know how to draw these graphs. And I should also mention that in the P2 course you definitely do need to know the graphs of cosec, sec and cot x. So needed for P2. And it's a very good exercise anyway for anyone to get used to these ideas. So let's start with cosec. Let's do a graph. Let's make a big graph on this sheet, and then we can work with it. So I'll draw. Oops, sorry, that was quite sure what happened there. Let's make a line, and let's make another line going across the way. Oops, need to grab that one. Okay, so there are axes, and just for variety let's call the angle theta instead of x. I'm going to try to draw, first of all, using a red colour, cosec or cosecant theta. Now we know that cosecant theta is 1 over sine theta. So we just have to think about the values of sine theta. When theta is 0, sine theta is 0, so this is not defined. When theta is 90, so let's mark, let's mark the key numbers here. 90, 180, and maybe 360 here. and minus 90 and minus 180, let's say. Okay, let's also mark the number 1 and the number minus 1. So when theta is 90, cosec theta is 1 over 1, so that's easy, that will just be 1. Oops, sorry about that. When theta is 180, well, we're back to sine theta being 0, so it's undefined again. But notice that if we took a small angle for theta, small positive angle, like 5 degrees, then sine theta would also be small and positive. That means 1 over sine theta will be large and positive. So it's going to get larger and larger the closer we get to 0. So we're going to get a curve like this. And the same thing will happen on the other side because sine theta is symmetrical about the line theta equals 90. So we're going to get again a curve going up to this. So let's draw a dotted line here to indicate that actually this graph never touches that. Now what happens between 180 and 360? Well, in this region we know that sine theta is negative, but apart from that it follows the same pattern as it did between 0 and 180. It's just the negative version of it. So the negative, so the graph will be just the negative version of the previous graph going like this. So that's the basic shape. And let me draw another dotted line. Obviously that shouldn't touch the dotted line. There we go. Let's just draw it going down like that. Dot, dot, dot. Okay, so we're going to get the same behavior on the left hand side as on the right, but just reversed. So between 0 and minus 180 we'll get a negative portion of the curve, again with its maximum at minus 1 and going to negative infinity. And then obviously if I add on, let's say around here, minus 360, I'm going to get again the same pattern repeating. Minimum at 1, curve approaching positive infinity on both sides. So that's the repeating pattern of the graph of cosec theta. Now let's use a different colour and let's draw the graph of sec theta. So I don't think it should take you too long to figure out what's going to happen here. I mean, don't forget after all that sine theta and cos theta are related in that they're only different by the formula cos theta is sine 90 minus theta. So the whole graph has the same shape, it's just shifted by 90 degrees. So to take a simple example, when theta is 0, cos theta is 1, so sec theta is 1. So sec theta, and when theta gets close to 90, cos theta gets close to 0, but it's positive, so we're going to go to positive infinity as we reach, whoops, let's change to a green colour. We're going to get it approaching, excuse my wobbly asymptote there, this is called an asymptote because it's a line which the curve approaches. Whoops, that's supposed to pass through 1 there. Okay. It's a little bit messy, as I expected, because my drawing skills leave something to be desired. So basically that curve needs to reach a maximum at exactly that point there. There we go. Okay, I don't think I'll do too much more because the graph is going to get messier and messier, but basically you can see that the same pattern's repeated, so that this, if I draw another asymptote there, this is at 270 degrees. There's going to be another curve for sec theta going from negative infinity, passing through minus 1 at 180 and then going down. And these curves will be repeated again and again. Now let's just, although it's going to be very, very messy, let's just look at cot theta. Remember, it's cos theta over sine theta. So we might just plot a few points in case you find this confusing. When theta's 0, we've got 1 over 0, so that's not defined. When theta's 90, we've got cos 90, 0 over 1, so that is defined. So if I put a big blue cross here, we know the curve crosses through that point at 90 degrees and y equals 0. And if we consider a very small positive value, then cos of a very small positive value is close to plus 1, sine of a very small positive value is close to plus 0. So it's a positive number, so it's actually going to come down here like this. And then if we do the same analysis near 180, we'll see because sine of a number near 180 is negative, we're actually going to get minus infinity like this. And actually this pattern will just repeat every 180 degrees. And oops, I wonder if I could just undo that one because that was really bad. It's just going to repeat every 180 degrees like that, and so on and so on. That will be repeated here and here and here. Okay, so I know that's all a bit of a mess, but what's the real point? My real point is you can draw these. Just think about it. And I say that because sometimes students seem to be very scared of drawing graphs, but it's really not very difficult. Just choose the key points, and if the function is not defined at a key point, for example here cotangent is not defined when theta is 0, then just consider a number very close to that point and ask yourself, will it be plus, will it be minus, will it be close to 0, or will it be close to infinity? And from those basic facts you should be able to work out anything you need to. Okay, so that's the graphs of those functions. Now let's go back to the syllabus. Sorry, that's not what we want. Let's go back to the syllabus there and remind ourselves what we need to know. Okay, the next kind of thing that we really need to focus on, I think, is this part here, which is how do we draw the general sine or cosine or tangent curve? We should already know how to draw sine, cosine and tangent, but how do we draw them with these numbers a, b and c? So let's consider a concrete example. Y equals 3 sine 2x minus 2. What is the amplitude of this graph? What is the period of this graph? And can we draw it? Those are the skills that we need. Oh, I should also say we need to be able to easily state maximum and minimum values of these graphs and where they occur. So how do we do this? First of all, amplitude. Amplitude of y equals sine x is 1. What do I mean by that? I mean that if we draw a sine curve, the distance from the top to the middle is 1. And of course that's also the distance from the bottom to the middle. So the amplitude is 1, not 2. Okay? Notice it's not the distance from the top to the bottom, but from the top to the middle. So the amplitude of y equals 3 sine x is obviously 3, yeah? Because it just means the maximum has become 3. So if this, the top here is f of x, well, we can see that fx has amplitude equal to 3. So if we were to draw fx, I'm just going to draw this quite roughly. Does it mean that fx looks like this? Is that right? So look again at fx here. Well, no, obviously that's wrong because it has a -2. So each point on this curve we should subtract 2. So let me draw that graph again. It's a bit messy anyway, isn't it? Let me draw that graph more carefully. So here's our graph, and just draw a little bit of a arrow there for x-axis. Don't forget to label your axes. We know that it has amplitude 2, so it goes up 3 and down 3, but each point is subtracted 2, so the maximum, if you think about it, is not 3 but 1. And the minimum is -3, -2, or -5 down here somewhere. So what's the center line of the function? Well, it's clearly where, how do I draw this? Maybe here. Okay, this is maybe not a very good scale. I'll draw this a little bit lower down. Okay, -5 is here. So that means our graph has a maximum at 1, a minimum at -5, and a center point at -2. And when x is 0, it's clear that y is -2. So the graph will definitely look like this, as a sine wave going up and then down, up and then down. Now, of course, the quality of my drawing here is not very good, but be reassured that your graph drawing doesn't have to be perfect, but it has to have a couple of qualities. It must be curves, not corners. So corners would be when you do this. Yeah, anything that looks even slightly like that on a sine wave will be given will lose marks on the exam. So be aware of that. But of course, you should still try and draw your curve a little bit better than mine here. That's just my limitations with this computer. So try and draw fairly carefully. Use a pencil if draw it as well as you can. Now here we are. We've nearly finished. We haven't quite drawn the graph. First of all, I should say that in the exam they will always tell you for what domain or what set of values of x that they want you to draw the graph. Obviously you can't draw it forever, so you choose a particular domain. So here I'm going to choose I'm told to go from 0 to 360 degrees. The only thing that's left is to decide how many waves do I have. So let me write that key question. How many waves? So if you studied this in physics, this should all be quite easy for you. This could be considered one wave because it starts and finishes in the same place. This would be 2 waves, and so on and so on. And of course the technical name for wave, or one complete, is called a period. So really what we're asking is how many complete periods. If you don't know what period means, or at least if you don't know exactly what it means this idea: f of x is periodic if it has the property that this is true. Now notice here I used the identity symbol to represent the fact that it should be true for every value of x. So sine x has what period? In degrees, the period of sine x is 360 degrees, and in radians it's 2 pi. So sine 2x has period 360 degrees divided by 2 equals 180 degrees. And that will always be true. I mean, you can try and prove it if you want to, that this number acts as a denominator here. So if this was sine 4x, then the period would be 90 degrees, and that would be true for any number. Sine 1/2 x, the period would be 720 degrees, because that's 360 over 1/2. So for that reason we see that between 0 and 360, given that the period, we've just decided, the period is 180, the amplitude is 3, so we see that there are 2 complete periods. So this is actually the correct answer, although very badly drawn. That's 1 period going up to 180, and that's 2 periods going up to 360. It helps, by the way, if you want to draw it well, it helps to mark out, and I might show you this so I'm not too much of a hypocrite. I'll actually show you how one can try to do it, even if one has very bad drawing skills. It can still be done reasonably well. Using a ruler can help as well, by the way. I can't use a ruler here to measure or to draw straight lines, but the first thing I would probably do if I was trying to draw accurately would be to draw a dotted line to represent the maximum, and a dotted line, oops, no, it's not there, sorry, a dotted line to represent the minimum. So, and then even further I might draw a dotted line to represent the middle point of the wave. Then I might mark on the position of each period, so 180 is about here. So now I see the boundaries of my graph. I know that it has to go for a complete period like that, and then another complete period like that. And although it's not perfect, it's a bit more of a rational way to do this. So consider doing that. Okay, so I'm not going to go through how to do the same thing for the case a cos bx plus c, but note again that a is amplitude. Actually, I should be careful. The absolute value of a is amplitude, because a can be negative, and the period is 360 degrees divided by b, or 2 pi over b if you're working in radians. Now let's maybe do a slightly more difficult case. Let's do gx equals 7 minus a half tan 1/3 x. How would we deal with this case? Well, we should know that tan x has period, well, you tell me, what's the period of tan x? The answer is 180 degrees. So So the answer is 180 degrees. Let me just get back to my window. Here we go. Now, amplitude, does this mean anything here? No, it means nothing, because tangent x doesn't have an amplitude because it goes to plus and minus infinity. So that would be meaningless. But let's suppose we were asked to draw the graph of gx for, let me see, x from 0 to 2 pi radians. Yeah, okay. So I'll put an equal there. So let's draw a graph of that. First of all, we recognize that we're going to have an infinite range here. So we just need to remember the basic shape of tan x and consider, so suppose here is 2 pi, this is 0, this is g, and now we need to think about the period of g. Well, g has period 180 degrees, or pi, divided by b. Here b is a third, so it's actually 3 pi is the period. Sorry, why did I put... okay, I might change that actually, sorry, let me change that to... change that to 1/3 and that to 1/2. Sorry if that's annoying to anyone, but it's going to work out better. So this would actually be 2 pi, not 3 pi. So I know now that I've got a complete period of this graph being marked out. Now when x is 0, tan x is also 0. So the starting point of my curve is 7. So let me mark 7 here, plus 7. Now I know that tan x would usually rise up like this, but now I have a minus sign, so it's going to go down. And I also know that when x is pi, then I'm getting tan pi over 2, which is undefined. So I'm going to draw a dotted line in the middle here to represent the point x equals pi. And I know that my graph, instead of going up to this line, is going to go down because we have a negative sign here. Basically, if we have a negative, it's just going to flip the direction. So this will go like this. And maybe I can draw this point here as the end point of my graph, like so. Whoops, that wasn't very good, was it? Let's undo that. Okay, so I hope you followed the logic there. Let me maybe just, in case anyone's struggling with it, let me make a little annotation or note. What I'm doing is I'm starting from this concept that I know the graph of tan x. It just looks like this, doesn't it? Where this is pi, or 180 degrees, if you're working in degrees. This is 0. This is tan x. So I'm using this basic pattern. The first thing I'm doing is I'm flipping it because of the minus sign. So I'm going down instead of up. So that if we had minus tan x, it would look like this. Yeah. Then I'm also using this number 7 as my starting point, because when tan x is 0, I'm going to get 7. So the whole graph is moved up by an amount 7. Now, interesting point is, what is the importance of this 1/3? The answer is, for this graph, the 1/3 doesn't matter. Of course, it does matter for any individual number on the graph. So if I wanted to calculate this point, you know, where this was, I don't know, 0.1 or something, then I would need that 1/3, but it's not going to affect the shape at all. So that, oops. So that was maybe an unusual example, but I hope it was helpful. You will need to probably, unless you're already very good at graphs, to practice things like, let me give you another example to think about. Practice drawing graphs like 4 minus 2 cos 6x or something like that. Yeah. Use the same principles that we've just discussed. Make sure you understand amplitude and period. Now it has to be mentioned that it might also be necessary to understand graphs like this, where we add what's called a phase shift, but according to the syllabus you're not going to be asked to draw that kind. It is obviously a bit more difficult, but if you can do it, that's all the better. Now let's look at the exam questions, and we'll just spend a little time on that and then finish. Okay, so exam questions. I think I'll just choose some of these kind of randomly. I think I'll start with this one. Let me just drag it into a convenient place. I haven't actually done these questions in advance, so excuse me if I make any silly mistakes, but I probably won't. This first one is a proof, so it shouldn't be too difficult. What we've got is something of the form left-hand side is identically equal to right-hand side, and the best way usually to prove these is to start from the left-hand side, because the left-hand side is more complicated. So the left-hand side, let's write it out, 1 plus sec theta times cosec theta minus cot theta. And all I'm going to do is I'm just going to keep changing it step by step in a simple way until the right-hand side appears. So let me use the definitions of sec theta, cosec theta and cot theta. 1 plus 1 over cos theta times 1 over sine theta minus cos theta over sine theta. And be careful, because sometimes the answer might seem very obvious, but you mustn't jump steps. You must show the examiner you're working. So here I'm going to try to so I'm going to try to make a single denominator. So I'm going to put a cos theta there. Cos theta plus 1 over cos theta, that's the first bracket, times 1 minus cos theta over sine theta. So according to the formula for the difference of two squares, this is 1 minus cos squared theta over cos theta sine theta, and this is obviously sine squared theta sine theta cos theta sine theta over cos theta, which is equal to tan theta, which is the right hand side. And now we can write QED, quod erat demonstrandum, because we've proved the formula. So that's the kind of level of detail you need here. Do not use less detail than that, because you're taking a risk. Okay, the next couple of examples, I'm going not to give you the exact answer, but just sketch out the method, because I don't have a calculator with me and I don't really want to do that. So I won't actually do the calculation at the end, but I'll just show you the method. Let me just drag this a bit further down. So I like these examples. These are very typical examples of the kinds of equations you'll be asked to solve in the exam. So let's look at the first one. The first one is, so let's say part A. So we have a certain range of values of x, and then we have 2 cot x equals 1 plus tan x. Now we're aware of the fact that cot x should be written as cos x over sine x. It shouldn't really be written as 1 over tan x, but having said that, there's no problem with writing cot x equals 1 over tan x in this question, for the simple reason that if either of these two quantities are 0, then the other one is undefined. So that means neither of them are 0, so this equation will hold. So I'm going to approach the question like this, although it might not be the only way. What I'm going to do is write, well, just for simplicity, let's call tan x u, because we know that cot x is 1 over tan x. So there we can write cot x is 1 over u. And the advantage of this is we change the equation into the form of a quadratic equation. 2 1 over u equals 1 plus u. Well, this is easy to solve. U squared plus u minus 2 equals 0. So that's... Now at this point you should always be very careful, because although there are two solutions, are they both valid? Well, let's examine what they mean. U equals 1 would imply tan x is 1. Well, that would imply x is pi over 4. Sorry, we're working in degrees. Always remember to pay attention to the examiner's choice. Here we have degrees, so we have 45 degrees. Now that's not the only answer, and just for clarity, you probably don't need to do this if you're good at trigonometry, but you could have a quick think about the shape. Well, that's not a very good shape. Have a quick think about the shape of the graph. This is 90, 90, 180, this is 270, and then this is 360. So from 0 to 360, oops, this is really appalling, isn't it? This is 45, sorry, this is 1, not 45. There are two possible answers, 45 degrees and 45 plus 180, which is 225. So we found two solutions to the equation. But what if u is equal to minus 2? Well, yes, because it's tan x, the range of the function is all numbers. So this is possible. And again, we're going to get two solutions. Yeah, minus 2. One here, one here. And the values of x will be inverse tangent minus 2, which is a negative angle, plus 180 degrees, and inverse tangent minus 2 plus 360 degrees, or if you prefer you could write 180 degrees minus inverse tangent 2. And of course you can use the calculator, and indeed you should use the calculator to find those values, but I won't do it now. Okay, let's look at the other question. Maybe I can make a copy of it. Yeah, I guess so. Copy. Yeah. So here's a copy, and we're going to look at part B now. Oops, sorry. So in part B we have the equation 6 sine 2y plus 1 plus 5 equals 0. Now notice the way they express the question. First it should be radians, our answer, and then it says two smallest positive values of y. So that means we need to think about whether the answer that we're getting is a positive or negative number, and then find the two smallest positive. So let's first rearrange the equation into a sensible form. Sine 2y plus 1 equals minus 5 over 6. Now, we know that y our answer needs to be bigger than 0. Let's define a new variable, theta equals 2y plus 1. So what's the restriction on theta? Well, theta, if y is positive, then theta is bigger than 1, and that's in radians, isn't it? So it's bigger than 1 radian. So it follows that what we're doing is, again, if I sketch roughly a graph, I should mention, of course, this means that sine theta is equal to minus 5 over 6. So let's draw reasonably carefully, if we can, a sketch of sine theta. Now there's no amplitude or period concerns to worry about here because I deliberately chose theta to be this, you see. So if this is theta and sine theta, I can draw theta bigger than 1. Now pi over 2 is about 1.57. So this point here is about 1.57. So 1, let me draw a red dotted line, 1 is somewhere in here. Okay, so we want sine theta to be minus 5 over 6. So I'm going to draw, now that's nearly minus 1, isn't it? So I'm going to draw a line down here somewhere, and I can clearly see that what I'm looking for are those two solutions. Now we've got to be a bit careful because, you know, again, if you understand sine functions and so on, there'll be another number here and another number here which we may have to consider in order to get this right. So let's first consider what would we be getting if we just use the calculator and write theta 1 is inverse sine minus 5 over 6. And remember, it must be in radians. You'll get a certain number. What will that number be? If so, again, let me say that clearly. If you put this on the calculator, which of these blue circles will you be getting? The answer is you'll be getting this one here. That's what your calculator will give you, because your calculator will give you a number in the range between minus pi over 2 and plus pi over 2. So the calculator will give you that number. So to get the number that the answers that you want, the first thing you need to do to find this one, a bit of a riot of colour here, I'm going to get the one over here from here by adding by adding 2 pi. So theta 1 is not actually a solution because it doesn't correspond to theta bigger than 1. Remember, our restriction was that theta should be bigger than 1. So forget about theta 1. Theta 2 is our first solution, and it's 2 pi plus inverse sine minus 5 over 6. So again, this is the number that the calculator will give you. Add 2 pi, that's our first answer. Now what about our second answer? What's an easy way to get that? Well, let me think. What's the easiest way to get that one? We can say that this number here is pi minus inverse sine, minus pi minus inverse sine minus 5 over 6. So this is a negative number. This is this negative number. If we add that number, so make it positive and add it to minus pi, we're going to get the other answer plus 2 pi. Hang on a minute, let me check that. Yes, sorry, so just double checking that. It's definitely correct that this gives you Another way to write it, of course, is to write pi minus the original angle, and we can call that theta 3. And our two answers are theta 2 and theta 3. These are the two smallest positive values of theta, and we should also just mention that the for each one of those thetas you can get the corresponding y. So for example, corresponding to this theta we get y equals theta minus 1 over 2, and the other y we get is, okay, so all of that can be done on the calculator, and you'll get the two smallest positive values of y, which solve this equation in radians. So that's how we do that kind of question. Just to sum up, let's have another look at the syllabus. We understand secant, cosecant, cotangent. We understand amplitude and period. We know hopefully how to draw these types of graph, although it needs practice. We didn't actually use these formulas, to be honest. They're not really very important, but I do want to mention that if you start with sine squared theta plus cos squared theta equals 1, identically equal to 1, divide it by sine squared theta, it gives you 1 plus cot squared theta equals cosec squared theta. That's this one here. And if instead you divide by cos squared theta, then you'll get the other one. So sine squared theta over cos squared theta plus cos squared theta over cos squared theta plus 1 over cos squared theta. Well, this will give you the other one, tan squared theta plus 1 equals identically equal to sec squared theta. So this will give you the other one here. So there's absolutely no need to learn these formulas. If you see something that looks a bit like it, be aware that you can use these formulas and quote them because they are given on the formula sheet. Okay, I don't think I'll do any more of these exam questions. It's probably not necessary, but of course you definitely do need to practice. I would say the most important thing to practice is the method of drawing graphs such as these ones. So do take a look at exam questions like this one, where it asks you to do things like here's the function, here's the amplitude, here's the period, calculate A and B. Consider the minimum value, find C from the minimum. So have a look at that kind of question. Alright, I'll stop it there. Thank you very much.